example 4, this is, again, a 4-type problem, but it's working with the compositions that we had yesterday. So I want you to do like an A, a B, and a C. We'll get some good practice in your notes on this. The first function that we're going to look at, I'm going to label h of x, and we're going to have 1 over 3x minus 1. Okay, so here's the function we start with. We're going to decompose this function, meaning I want you to find the 2 original functions that made this up. And there's actually more than one right answer here, but I'll kind of walk you through each one of these examples, and then when you practice this tomorrow a little bit more, then we're going to, obviously have more right answers that we can pull from and I can show. But I'll at least do the more obvious ones here. Okay, so if we were to back up, I do know that this was created by some type of composition. So I'm going to say, well, I'm looking to see what f of g of x would have had to be in order to get that. Well, one that maybe some of you are even already thinking about now is if I let f of x be 1 over x and g of x be 3x minus 1, those would be 2 different functions, and that one would be created by taking 3x minus 1 and plugging it in for x. The nice thing about decomposing a function is you can always double check and see if it works by actually doing the composition yourself. Okay, let's do minus. Okay, so this one's a little bit more difficult. Again, I know that 2 functions made this one up, so I'm going to try to think through what would have had to be plugged into the other to come up with this function. Now, I might start with the basic premise of, let's make it x squared minus x. Kind of see that format here. And then maybe, in order to get a 9x squared there, I would have had to plug in a 3x. But then if I plugged in a 3x here, I wouldn't get 15, so I'd have to put in a 5. And so if I did it now, if I plugged in 3x squared would give me 9x squared. And 3x into that x, because you have to plug it into both, would be negative 15x. So yeah, that would be one set of correct problems in order to compose a function and get a new one. Okay, let's look at one more. Okay. This one might be a little bit more obvious than part B there. But again, we're looking for the 2 functions that make up this original one. So you kind of see the framework. The framework would be 3 times x squared minus 4. And then we could replace the x with that 2x plus 1. And again, we can just double check. If I was to take this and plug it in for x, I would get what I started with. Okay. Now usually I do that type of problem with the whole group, kind of talking through it, and we will do more of these tomorrow, obviously, and talk through it together, but at least that gives you 3. You can kind of hear my thought process through it, and maybe when we try it tomorrow, you'll be a little less intimidated by it. Okay, for example 5. This is another 4-type problem. It's actually applying composition to a real-life scenario. You have a $10 gift certificate to iTunes. iTunes is offering 15% off your entire purchase of any music or movies. You decide to purchase $30 worth of music and $25 worth of movies. We're supposed to find the sale price of your purchase when the $10 gift certificate is applied before the 15% discount. Okay, so let's actually make our 2 functions, because we've got to have 2 to work from. So we have to have one that represents the discount, and one that represents the gift certificate. Let's make f of x our gift certificate, and make g of x our discount. Now, a gift certificate, the unknown is, well, we kind of know it, but if we didn't know what we were actually going to decide to purchase, our unknown we would label x. So x is going to be money spent. Or I should say money, sorry. Y is going to be the final price. Yeah, and maybe we'll just put money for price. Original price. There we go. Original price. Alright. So in order to write the equation that represents your gift certificate, it would be the original price of whatever you're purchasing minus $10, because your gift certificate is $10. When you apply discounts, like to find 15% of 100, you'd multiply 100 by 0.15. So if our original price is x, we're going to multiply that by 0.15 to get my discount function. Now, if we want to find the sale price, if the gift certificate is applied before the 15% discount, what you're finding is g of f of x, because then the $10 gift certificate would be applied before the discount. Okay, so let's go ahead and plug that in. I'm plugging f of x in for x in the function g, so I'd have 0.15 times x minus 10, because that whole thing is going to replace the x. Okay, so this is this scenario. And if I know the original price of what I want to buy is $30 and $25, that's a total of $55. So then I'm going to find what I would get if I plugged in 55 for x, which if you do that, you get $6.75. So the sale price would be 55 minus $6.75, or $48.25. Right. Hold on. Sorry, I messed up there. That shouldn't be 0.15, that should be 0.85, because this is representing what you're actually paying. Like, that doesn't make sense. Okay, let's try that again. Alright, so 0.85 times 45, oh, that's better, 38.25. The reason I knew that wasn't right is because 48 was not even $10 less than 55, so that's not even the gift certificate price. Anyway, that makes it better. Alright, and then for B, find the sale price of your purchase when the 15% discount is applied before the $10 gift certificate. That's just reversing the process here, so we're going to find f of g of x. So we're going to plug the 0.5 or 0.85x into the other function for x. So you should get that scenario. And then again, we're going to plug in 55. And you get 36.75. Okay. Now, the reason this would be helpful is because there is a $2 difference almost between the two, and it's all in a matter of what you use first. So, if you have ever seen anything like on the Coupon Wars or people that are professional couponers, they figure this stuff out and know if I give this to them, they take that off first, and then I give this to them, and they take it off, and then I give this to them. Like, there's a certain order you have to give stuff in order to get the deepest discount. So that's good to know. If you have a gift certificate and there's already a sales price, make sure they do the sales price first and then take off the gift certificate, and you'll save a little bit more money. Okay, go ahead and flip. We're going to at least touch on or start the next standard. Alright, for F2, I can write the inverse function when I'm given the original function. That's what we're going to focus on today. And this leads into our next unit when we have to talk about some inverse functions. Alright, so this standard is also nice in the fact that you have used inverse functions, or at least inverse operations, your whole mathematical career. You've just not been aware of it. An inverse function is a function that undoes an original function until only x is left, or whenever your variable is left. So I'm going to briefly talk about some inverse functions or operations that you already know. Some of them you already know are squaring and square rooting. Those are inverse operations or functions. Adding and subtracting. Those are inverse operations. Multiplying, dividing. Those are inverse operations. I mean, we could say cubing and cube rooting, because we've kind of talked about that. What are some other ones? Perpendicular lines and parallel lines. And then we'll actually be able to add to this after the next unit, but I think that'll be a good prep. The point in bringing up this list is just to show that you already know some of these inverse functions and operations, and now we're going to actually apply them to different functions. Okay, so steps to writing the inverse function, because since that's what the original standard is talking about. You're going to write your original function, and if you need to, replace f of x with the variable y, just because it'll make the next part easier. Then you interchange the x and y. Basically, you flip the position of them. Because with inverse functions, everything is completely opposite. So the x and the y we're going to completely flip around. And then your third step is to solve for y. And then we usually label the inverse as f to the negative 1 of x.
Please excuse this interruption. This message is for sophomores and juniors. If you are interested in learning about the new Career Center programs in pre-engineering or information technology, please report to Mr. Goubinot's room today during advisory. Again, that's for sophomores and juniors only. Thank you.
Okay, we're just going to do one example together here, and then we'll call it good until we practice this a little bit more tomorrow. With writing an inverse function, if I give you this linear function and I want you to write the opposite function to it, so basically one that would undo this one, we're going to start by writing f of x as a y. And then with inverse functions, everything is completely opposite. So we're going to take the x and the y and we're going to flip them around. Just like that, interchange them. And then we're going to solve for y. So to get y by itself now, I'm going to have to subtract 4 from both sides. And then multiply by 3. When I multiply by 3, I get that. So I can simplify to get 3x minus 12. And then if this is the inverse function, I want to label it as f to the negative 1 of x. This is just like the inverse notation. So if ever you see f to the negative 1, that's saying that this is the inverse function or the opposite function of something. would be the example. Now, why this is an inverse function, or that it undoes the one that you had before, just real quick, is if I was to plug in or compose f of g of x, so plug one into the other, if I distribute the 3 through, I get x plus 12, and then the 12's cancel. That should happen every time with inverse functions, is that if you make the composition, so you plug them into each other, you end up getting just the variable because everything else cancels out. And we'll pick up there tomorrow.